Okay, so this is review session 2, I believe. Today is 9/11, and we have quite a few things to go over today. Namely, you've learned two of the kind of core skills in the class, node voltage, and actually, if you've not learned mesh current yet, you might have not learned mesh current yet. I think you haven't learned mesh current yet. So I'll go over node voltage, I'll go over source transforms, and I'll go over voltage and current division mainly, because those are the most useful things you could be learning right now, in my opinion. So to start, um, I'll go over source transforms, which I think you learned last week, but wasn't really on the quiz. It will almost definitely be on this quiz, I would guess, just because it's an important thing to know. And the general idea with the source transform, hopefully you saw this on your homework, is that there is a direct equivalence between two circuits that look kind of like this. That's a resistor. Sorry for my drawing. But if we have a voltage source in series with a resistor that is functionally identical as a current source in parallel with a resistor. And so let's say this has some voltage V, this has some resistance R. What we end up finding is that this current will be V over R, and this will have that same resistor. This is useful because it allows us to simplify some circuits that would be very complicated to do otherwise. Likewise, if we were to have some current here, I, then to go back, the voltage would be equal to IR. Wow, you've seen that before. So that's that. I will do some practice problems. I'll go over that practice problem from the homework that had that because I saw some people had difficulty with that. And I think that's a good example of how to apply source transforms. One other thing to keep in mind here is that like the direction of the voltage source is going to be the same as the current source. So if it's from minus to plus in this direction, the current source will end up being from minus to plus in that direction as well. One other drawing I'll make real quick is just a different way you could look at this. So you'll notice that when I'm done with this, all the connections will be exactly the same. It's just drawn in a different shape. This up a bit. So this might be a bit more clear, but this is the exact same drawing, or it's the exact same circuit, just drawn in a slightly different way. So we still have V and R, and we still have V over R and R. And this this is the same as this is the same as this. So those are just different ways that you can draw this same circuit, and all of those can be useful in different ways in different times. So that's the first topic I wanted to go over. Next, I'll go over voltage division. This is kind of a shortcut for a lot of your like circuit solving problems. I personally think this is like if you understand this well, there's a lot of questions in this class that you can probably just do in your head, and it makes your life a lot easier. Basically, the idea is if we have some voltage source and it's connected to a bunch of resistors, let's say this is 20 volts and this is 4 ohms, 6 ohms, 3 ohms, and this is 2 ohms, right? And we want to say, okay, what's the voltage across each of these resistors individually? Or what's the voltage across like a portion of them? The general idea is that for some given resistor, I'll look at this 6 ohm resistor. The voltage across that 6 ohm resistor, that's a G, not a 6. The voltage across that 6 ohm resistor is going to be equal to the input voltage, which I'm going to call this the V in, just because that's some terms you'll hear later in the class. It makes a bit more sense. So it's going to be that input, which in this case is 20, times, or I'll do it explicitly in numbers first and then give a more general formula in a sec. So it's going to be that input 20 volts times that 6 ohms over the total resistance. So 4 plus 6 plus 3 plus 2. What you can think of this as is, okay, there's some total resistance if you were to add all of these together, right? And that total resistance, the voltage across it, would be the same as that 20 volts. However, if we are just looking at the 6 ohms, we can think of that 6 as some proportion of the total. And if the total gets 20 volts, the total voltage that the 6 ohm resistor will get, when I say get, it's like kind of it's not like it really gets it, it's just what ends up being shown. But in my head, it makes sense when I say get, so that's what I'm going to keep saying. So the total voltage that this would get is equal to the proportion of this to this times that input. So that's what this is saying. If you want this in very explicit, nice math terms, you can say like the voltage of some resistor is equal to the input voltage times that resistance over the total resistance, or like V in R over R1 plus R2 plus dot dot dot, you know? And this is very useful all the time. Um, for example, if I wanted to, in this scenario, let's say the question was like, okay, find this voltage, right? You can just do the same thing with that 2 ohm resistor. Or actually, I'll do it with do it here, right? If it was asking you to find this VA, right? You could think, okay, I know there's 20 volts on that input, right? And here, from here to here, I have 3 plus 2 volts, or 3 plus 2 ohms, because they're in series. So I can do the same thing, right? Here, VA would be equal to that 3 plus 2 over 4 plus 6 plus 3 plus 2 times that 20 volts. So here, I should actually get out my calculator and fill in all these numbers. Give me a second. So for that first one, when it was 20, it would be 20 times, oopsies, 20 times 6 over 4 plus 6 plus 2 plus 3. So this would have been 8 volts. And here we have a similar thing, but now instead of 6 on top, it's going to be 5 on top. Um, we get 6.67 volts. So hopefully that's pretty clear.
I have a question.
Yeah.
So let's say if we had like a branch of resistor in parallel
Mhm.
connected to that six resistor in like that branch that has like resistors in parallel was connected to that six resistor, which is the one that we are looking for at voltage, what would we do?
So if you had something like this, is that what you mean? What I drew here?
Yes, yes.
Okay. So what we'd have to do then is, so you're correct in asking that. This only works when you have resistors in series, right? So here, in order to find the voltage at this point, so if we had like this, then we would need to combine all of these resistors into one equivalent resistance for that section. Basically, we'd need to turn this into something that looks like this. So I can give a brief example on that. Let's say this was still 3 and 2, but then this was like 7 and 4, okay? Then before we can find that VA, we'd want to combine all of this. So to do that, okay, 7 plus 4, I'll just focus on this section. So you have the 6 there, and then 7 plus 4, right? That's going to be 11 ohms here. And then 3 plus 2, that's going to be 5 ohms here, right? And then we learned for resistors in parallel, it's going to be R1 times R2 over R1 plus R2. There's a couple different equations. That's the same as like 1 over R1 plus 1 over R2, however you want to think about it. But then we'd get 5 times 11 over 5 plus 11, which would be, this doesn't look like it's going to be a nice number, but we'll see. So 55 over 16. Yeah, okay. These are just numbers I'm picking randomly, so I'm not surprised that they don't look nice. But so you get that, right? So then, sorry, I'm running out of space so horrendously here. But what that's saying is that, so we turned these two into this resistor, we turned these two into this resistor, right? And now we're turning these two into this resistor. So this would end up becoming, if I go down here, 3.4375, 6 ohms, 4 ohms, and then we'd still have that VA at the same point because these 2 points haven't changed at all, right? This here was still this here is still this here. This here is this here is this here. So then once you have this, you can do voltage division just in the same way I described earlier. So the answer to your question then is just if there's other branches, you have to combine them until you get something in series. Yeah. Okay, next up, I will talk about node voltage, which is probably one of the other most useful things you will ever learn in this class, or in terms of like the rest of the class. Forgive my roommate laughing very loudly in the background. I have no idea what he's probably looking at Instagram Reels. Um, anyways, where's a good drawing I can pick for this? Um, I'll just take the one that she did in class, actually. Um, no, I'll take one from a different thing. So the general idea with node voltage is that uh, if we have a lot of unknown stuff, the easiest way to, if we have like a really big circuit and there's a lot of things and we don't know where to start, the easiest way to go about it is to just write a bunch of equations and then solve them. So like node voltage deals with Kirchhoff's current law, which if you remember is saying that the current going in is equal to the current going out, or you can write it as the total currents in a node equals zero, or you can write it as, yeah, so a bunch of different ways to write it. I'll give this very big circuit. Oh, and another key thing is that in is negative and out is positive. This will be very important here in a sec. Um, but basically, if we have a really big circuit like this one, I'm going to spend a minute drawing here. So if we have a really big circuit like this, and you were to say, what is this voltage? And you were told to find that, right? There's so many places you could start, so many things you wouldn't really know what to do. What node voltage is doing is basically saying, okay, we can just look at the junctions or the nodes, they're not junctions, but if we can look at the nodes where we have actual like junctions happening, so that would be nodes where there are three components touching each other. So here, here, and here, pretty much. And we can write KCL equations for each of those, and then we should end up with three equations and either three or fewer unknowns, and then you can solve for all the values you want. So the way that works is we want to start by declaring 1 point on the circuit as 0 volts, just so we can have something to reference with the rest of it. And usually for this class, your circuits will be drawn such that the bottom is 0 volts. Generally, you want where as many components as possible touch to be 0 volts. So if you look, this bottom node, it's touching here, 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 and here. That's 5, whereas all the other ones are only touching like 3. So that's why we'd end up selecting this as 0 volts. And since voltages are all relative, like you could pick anywhere, but this is generally going to be the easiest way. Then for the other nodes in our circuit, we're going to label them V1, V2, V3. And one key thing that I will point out is that, actually, I'll go over that in a minute. So basically, we want to do a KCL equation at each of these nodes. So I'll start with V1, right? So if we look at what's coming in from the left here, we will have negative. So when you're doing this also, just ignore all the variables. Just write it as explicitly as possible. Just leave it in the equation form, and then you can deal with making the equations look nice later. So here we'd say, okay, minus 5 I naught. Wait, where's I naught? Which one's I naught? Give me a sec. Forget in this drawing which one was defined as I naught. Um, oh, okay. Sorry, this is I naught. So here we'd have minus 5 I naught because this is a current source going in. And then when you have things with resistors, my personal recommendation is to always assume that the currents are going out for a resistor, even if you don't know which direction it's going. So like for V2, we'd also say all three are going out. What'll happen here is if this current actually ends up going that way, then you'll just get a negative number, and that's fine. But when you leave everything as going out of the node, your equations will have a lot of positive numbers, and that makes your life a lot easier. So, however, when you have a current source telling you the current is going that way, you can't pretend it's going that way because you're just wrong. So,
But then in that case, you already have like two currents going in two directions, like where the 5 ohm is.
mhm. Yeah, so that's fine though because this will be in like two separate equations, and what'll happen is like this one will end up being positive and this one will end up being negative. So if this one's negative, then it's telling you that it's actually going that way, and it the math turns out fine. In your drawing, it looks a bit weird, but I can assure you, like if you do it like this, the math will be so much easier, and you will thank yourself for it. I'll show you what I
Mhm.
mean in a sec though. So for V1, yep, we have, oop, my Apple Pencil, hopefully that doesn't die. So we have minus 5 VI, minus 5 IO going into the left, and then down, since it's out, it's positive, and the voltage here is just going to be V equals IR. This goes to I equals V over R, and in this case, V is going to be your V1 minus whatever that other node is over the resistance, because we have a voltage difference between here and here. We know the voltage here, or we've defined it as V1, and we know the voltage here, we've defined it as 0 volts. So here, this will be plus V1 minus 0 over 20, and then out to the right, we'd have V1 minus V2 over 5. And you can write ohms and ohms, and that equals 0, right? Next up at V2, we would have, starting at the left, we'd have V2 minus V1 over 5 plus V2 minus 0 over 40 plus V2 minus V3 over 10, and that equals 0. So with what you were saying about the arrows pointing in opposite directions, if we look at this term and this term, right? So we have in the first equation, we have V1 minus V2 over 5, and in the second one, we have V2 minus V1 over 5. If we look at this, this one equals negative of that one, right? Because you just flip these around. And what that's telling you is that even though we're like in our math, we're saying that both of these are going out, one of them is in the opposite direction of the other one. We don't know which one yet, but we know that from our equations, one of them will be the opposite of the other, so this will still work. Okay, moving on for V3, if we look at this, again, everything's a resistor, so we can just assume everything's going out for our math. And we'll get to the left V3 minus V2 over 10 plus V3 minus first. So this is going down. Okay, so this is where you have to think a bit, right? So here, it's not just going directly. So with V2, right, it was V2 and 0, and that was the two sides of our resistor. Now we have V3 and whatever this point is. This point, though, we do know explicitly the voltage of. If you remember, a voltage source is telling you, okay, from this side of my voltage source to this side of my voltage source, I have, say, like 10 volts difference. So if there's some voltage here, we know that this point is 10 plus whatever that voltage on the bottom is, right? Now I'll leave that up for a sec. So when we see a situation like this and we want to say, okay, what's the voltage right here? At the bottom here, we know it's 0 volts. So that means right here, by definition of this being a voltage source, we have 11 IO volts. And similarly over here, for this current going to the right, right, it's going to be this voltage minus this voltage. And this one is, okay, 0 volts down here plus 96 volts. So we end up with 96 volts up here. And that will be that. So for the current going down, we'd have V3 minus 11 IO, or I naught, over 5. And going to the right, we'd have V3 minus 96 over 4 equals 0. And then if you were to try to write out all these equations, you'll notice here we only have 3 equations, but we have 4 unknowns right now. So you would need to write in a fourth equation to figure out what that I naught is. And that's pretty simple. It's just if you look here, we've actually already written the term before. I naught is going down there, and that is the same as this one right here. So I naught is just equal to V2 minus 0 over 40. And then you could use whatever algebra method you wanted to solve for all of these voltages. And the reason that we do this is because this is a very nice systematic way to solve a circuit where you don't need to do that much thinking on the front end. It's just kind of write the equations in a way that is reproducible, and then you just have to do algebra. And depending on how nice the teacher is, I don't know how Dunning will make her quizzes as opposed to Zorman in the past. In the past, Zorman would sometimes have ones where you just had to write equations, but I don't know if that's going to continue or not. So I would definitely make sure you're practicing your algebra. Since it is a quiz, you probably wouldn't have something as big as this. You might have something with only 2 nodes, so you only had 2 equations to solve. But generally, solving equations in this way, it like takes a lot of the guesswork out of how to approach it. You can just write down some node equations and solve them, and then you get your answer.
Excuse me, can you please go over where you got the formula for I naught again?
Oh, yeah. So in this circuit, I naught was defined as this current, right? And so the current through this part of the circuit, remember V equals IR, this tells you that I equals V over R. So I naught in this case, right? I naught is going to be equal to, we can think of the voltage on the top minus the voltage on the bottom over 40, right? The voltage on the top is V2. The voltage on the bottom is 0 volts, and the resistance is that 40 ohms. So that's how we got that. It's the same way we were looking at it when we were looking at the current coming out of V2. It's just since we wrote some of the equations in terms of I naught, we have to define I naught somewhere. Yeah. Okay. So what else was on the homework that I wanted to go over? Let's see. Um, oh yeah, I wanted to go over that long source transform question just to make sure people are clear on that one. So this question, you all should have seen it on your homework. Basically, we had a lot of things kind of in weird orientations, and it was asking you to figure out what the current was going through a resistor at the end of it. So it was asking you, what is this current? And this was 2 ohms, 3 ohms, 6 ohms, 30 volts, 2 amps. That's not an amps. 2 amps, 4 ohms, 4 ohms, and 3 amps. So to do this, basically the goal is to turn this into one loop where it's very easy to find that current. So to do that, we basically just have to do a lot of source transformations. One thing I will say is it can be helpful to think of this by rewriting it informs, or redrawing it informs where it will look more like this. Because right here, it's a bit confusing as to what points you would cut off your source transformation. Whereas if we redraw it to look a bit more like this, it'll become a lot more clear. So I'll do that really quickly. And hopefully you all can see that this is the exact same circuit. It just looks a bit more like compartmentalized, and it should be a lot clearer where you would actually do those source transformations. So if you look here, all of the points on this circuit, they have all the same connections. I've just changed what the wires look like. But all of the connections here, so like this connection here is the same as this here. And likewise, this here is the same as this here. All of the same points on the circuit are connected. It's just the wires look different now. And hopefully now it's pretty clear to see, okay, I can do a source transformation here, I can do a source transformation here, and I can do a source transformation here. So let's do that. So for this first one, I'm just going to not copy the values down from the top because I don't want to. So this first one here, if we remember, so if we had some current here and we're transforming it back this way, then V is going to be equal to IR. So here, this first one on the bottom or on the left side would end up with, okay, it was 2 amps and 4 ohms, so that'll give us 8 volts. And the resistor stays the same, so we still have 4 ohms. Then going up to the next one, remember we have to keep in mind the direction of the current source. So the current source is pointing up, so then now we're going to have minus plus going up that way. And likewise for this one, and then this one will actually be the other way around because the plus minus is pointing in the opposite direction. Yeah. So here it was 3 times 4, 3 amps times 4 ohms, so this will be 12 volts. And then this is also 4 ohms. And then here, that 6 ohm resistor on the top does not change. However, this bottom part here will split into 2 branches because it's becoming parallel. So we have the resistor, which is 3 ohms, and we have the current source now, which is pointed to the left. And remember, I equals V over R. So this will be 30 volts over 3 ohms, which will give us 10, 10 amps. Then that goes through this 2 ohm resistor, and we're still not done because we still have a branch here, but this can be recombined pretty straightforwardly, right? So if we just look at this part in isolation, right? We have 2 resistors in parallel with a current source pointed that way. This was 6 ohms, this is 3 ohms, 10 amps. And these two can be combined the same way we showed before. So it's going to be 6 times 3 over 6 plus 3, which is going to be 18 over 9, which is going to be 2 ohms. So this thing equals this, where we have 2 ohms and 10 amps still. And then this can be turned back into a form that looks like this, right? So basically here, we took this, made it into 2 parallel paths, then combined the resistors, and now we're turning it back into just a single path. So if we do that, what we end up having is, okay, 2 times 10 is 20, and now the arrow is facing the other direction, and we still have that 2 ohms. And that's our circuit, right? And now that we have this, this is pretty trivial to figure out the current in. Since they're in series, we can kind of move them around however we want. since components in series, the order doesn't matter in terms of current. So this is equal to like having these three kind of just next to each other, and then all the resistors over here. And we actually end up with this specific question having a kind of funny situation where we go, okay, up 8 volts, up 12 volts. So here we'd be at like from here to here, we have 20 volts. But then here we go down 20 volts. So what we end up with is that this whole thing actually has 0 volts. So if we think about adding all of these voltage sources together, the equivalent voltage is just 0. And if we have 0 volts and current equals voltage over resistance, and we have 0 over resistance, then our current will be equal to 0 amps. So that's the fun answer to that question. But basically, that process could be used for any question, though, where you do not get 0 as your answer. But hopefully, that was a pretty clear example of how we can think about our source transforms to solve problems a bit better. Okay, moving on. Let's see. What else? What was I going to go over again? Let's see. I think the main things are going to be, judging from like your lectures in class this week, probably going to be mainly node voltage and such. So, but I'm never 100% sure though. Um, oh yeah, one thing I wanted to touch on with node voltage is something to watch out for. So I will make up this circuit as I go here. But let's say we have something like this. Let's say we had a circuit like this. Or let's put one more thing over here. So let's say we had a circuit like this. I won't actually fill in the numbers because it doesn't matter for the purpose of this example. But if we wanted to write node voltage equations for this, then we first have to start by defining some zero voltage point. So again, we want to define that as the point where as many nodes as possible are connected, or as many components as possible are connected. So here, that would be the bottom here, because this are all connected together at the bottom. If you're not clear as to why that is, like you can think of this as being drawn as like all of these meet at this same point. And so this would be your 0 volts. This symbol means ground or 0 volts. You might also see like, if you see this, or you see this, or a teacher writes it fast and goes like that, these all just mean 0 volts. So then, yeah. So once we've done that, so let's say this is 0 volts, then we need to define our nodes. And remember, the nodes are where more than two components meet. So, or the important nodes here where more than two components meet. So we have one over here, right? Because we have this, and this all meet there. And then we have one here, right? Because we have this, but then we also have these two, right? So what that's saying is that all of this is just one node. So one thing that a lot of people end up doing on their quizzes is they will try to have a node here and a node here. And then when they get to writing their equations, they get very confused because there's no resistor right here. And so they'll write like V1 minus V2 over 0. And then it's like, what? That doesn't work. So please be very careful about not doubling up on one node. So for this example here, when you were doing this, right, this would be V1, this would also be V1, this would also be V1. They're all the same. This would only be different over here being V2 because there's an actual resistor here allowing this voltage to be different from this voltage. So in that case, I'll fill in some like dummy values to show how you would maybe write this equation. So let's say this was 10 ohms. Let's say this was like, I don't know, call this I naught, 3 I naught, and this was 4 ohms, and this was 2 ohms, and this was 3 amps, and this is 6 ohms. This is 2 ohms. So at V1, we would have going out to the left here. Oh, actually, this is a bad question because that's already defined. Hold up. So the reason this is bad here is because since I put a voltage source here, that's explicitly telling you that V1 would be equal to 3 I naught. Hopefully that's clear for the same reasons I said before. Since this is a voltage source, it's telling you that, okay, between this point and this point, there is a voltage difference of that much. So pretend this wasn't a voltage source because that kind of breaks my example. This is another resistor. Yeah, and this is 4 ohms. Okay, so this here, going out to the left, we'd have V1 minus 0 over, or, okay, so remember all of this is V1, so we have this going out, this going out, this going out, and this going out, right? So we'd have four things for this V1, which is why it can look a bit odd, but it's all okay, and it works out in the end. So going to the left, or going in that leftmost branch, we'd have V1 minus 0 over 10, and then in the middle, we'd have V1 minus 0 over 4, and then another one, V1 minus 0 over 4. And then going out to the right, we'd have V1 minus V2 over 2. And that'd be fine. And then for V2, we'd have to the left V2 minus V1, because remember, this is still V1, over 2. And then coming up from the middle there, since it's going in, we have minus 3 amps. And then out to the right, we'd have V2 minus, oh no, we have, I don't know what that is. However, since you know that you can add resistors, we can just think of this as, okay, we have V2 here, and here we have 0, and then between them we have 8 ohms in total, right? So we can think of this as V2 minus 0 over 8 equals 0. And then this you could solve to find your numbers, right? We know algebra, we have two equations, two unknowns. You solve this however you like to solve algebra. And yeah, gonna take a sip of water. Now I still have like another 20 minutes, so I'll just do some practice problems. Yeah, this looks good. Okay. Yeah.
Could you go to not the question before, but the question before that and explain how you went from the first circuit to the second one?
So from here to here.
Yeah.
So the key thing here is that I did not change the circuit at all. I didn't do any source transformations. I just kind of redrew the wires, right? So with this first section here, right? Looking at it from the bottom, right? This point, so I'll start by like talking about this here, right? This wire going in is connected to the bottom of both of these, right? As long as that stays true, it doesn't matter how you draw the wire. So instead of being like that, it's just like that, right? So that's what this is. Likewise, as long as all the connections stay the same, it doesn't matter how you redraw it. So here we have this touches, this touches, this touches, this touches, and then they're all connected by a wire. It doesn't matter the shape of the wire, it's just as long as they're connected. Here we have the same thing, right? These four components are all connected by a wire. I just redrew it like this because compartmentalizing each of these like current source resistor pairs into their own separate section makes it make more sense when you go to do a source transformation later. Again, that's the same thing here. This is connected, this is connected, this is connected, this is connected. It's all one wire, and that's the same thing here. When I say one wire, I just mean like they're all connected only by wires with no resistors or anything between them. Because if you think to your like lab part of the class, if two things are connected by a wire, then there's no voltage difference between them. And that's the same thing here at the end. Again, it's like what I did for this section. Instead of looking like this, I made it look like that. And here, instead of looking like this, I made it look like that. Right? Cool. Hopefully that helped. And I will go on to the next part. Okay, so here, give me a second to draw this circuit. Okay, so this is saying find the power associated with the 2 amp source. So it's not saying power generated or power dissipated. So we don't know if this is consuming or producing power. We have to figure that all out. And it's saying do it using the node voltage method. So for this question, we want to start by defining our ground and then defining our nodes. So use node voltage. So our ground, generally, like, unless your teacher's being really mean, which I don't think Professor Dunning uh, is usually a safe bet to just put it at the bottom of the circuit. For this specific case, as I was saying, like you define it as to make your math the most easy, you want to define it as where as many components as possible are touching. And by that I mean like what I was saying back here, where like here we have 4 things touching. In this case, there's actually only 3 things touching on this bottom path, so it would be just as good to put ground here or to put ground here. It would all be the same, but just for like simplicity of looking at it, it makes sense if 0 volts is on the bottom because it's 0 and it's going to be the smallest number. So then we want to define our nodes. So the nodes again are where 3 components meet. So we'd have here, here, and here, right? However, before we get ahead of ourselves, before we label this V1, we actually know the value of this explicitly. Again, a voltage source, it is saying between this point and this point, it goes up by some amount of volts. If it's 10 volts, then on the bottom, if we have something, on the top, we have something plus 10. Here, on the bottom, we have 0. So then here, we just know we have 10 volts. You don't have to think about that at all. It just works. One thing that will also make this point clear is the symbol for a battery is like this, right? You might have seen this before. And if you think of this, it's basically telling you it doesn't matter what happens in the middle here. We have a difference of 10 volts between this side and this side. So really try to drill that into your head. The way I like to think of voltage and current sources is it's telling you, you don't have to think about this. We are telling you, for a voltage source, we are telling you between this point and this point, between this point and this point, there's 10 volts. And for a thing like a current source, it's saying, doesn't matter what the voltage is here, doesn't matter what the voltage is here, there is 2 amps flowing through this wire. So keep that in your head. It'll make your life a bit easier in the future. Anyway, we've labeled that one. This one we don't know anything about, it's V1. This one we don't know anything about, it's V2. And again, our goal is to find the power of that 2 amp current source. That tells us that we need the voltage of the 2 amp current source and the current of the 2 amp current source. Of course, this is going to be 2 amps because it's a current source, it's telling us, but we need to find that voltage. Before I get into actually solving it, let's define what that voltage would be, right? So if we want it to be positive, remember our passive sign convention, the power would be positive if the current is in the same direction as the voltage drop, right? So then here, a positive voltage would be this voltage minus this voltage. So in that case, we're going to say that the thing we're actually looking for is going to be 10 minus V1. So that's our goal. But to do that, we need to find V1. And to do that, we're going to use node voltage. So at V1, if we are doing a KCL equation, one kind of confusing thing about this part of the class is node voltage uses KCL, which is the current law. So it's a bit odd. And then you'll learn mesh current probably next week, which is similar, but that one uses KVL. So make sure you don't get those messed up. Why didn't that delete? Whatever. Okay, so here at V1, same thing we've done before. So we know this current is going into the left, and then since we have resistors on the other one, we're just going to say that they're going out. Likewise, for here, we're going to say that they're going out because everything's a resistor. Oopsies. Um, take a sip of water. So at V1, coming in from the left, we have minus 2 amps because it's going into the node. And then next up, we have V1 minus 0. This is the path going down over 2 ohms. And then to the right, we have V1 minus V2 over 2 ohms. Again, I think this was a previous quiz question when I graded this last year. Some people got very confused about this and tried to do like V1 minus 10 over 2 amps. And this is just, don't do that. Make sure you're actually thinking about, okay, each of these terms should be a current, right? So here we have voltage over resistor, it's a current, voltage over resistor, it's a current. Make sure you're actually like thinking about what it means as you're doing it and not just writing the equations. So anyway, that's our first equation. Then at V2, we have, okay, going up, I'll start with the one going up here, right? So here we have V2 minus 10 over 2 ohms. As if we're going that way. If this 10 was right here, that'd be pretty clear. If the 10 was right here, it would be pretty clear. But it's the same thing as like this situation, it's just drawn differently. So we'd have V2 minus 10 volts over 2 ohms. And then to the left, we'd have V2 minus V1 over 2 ohms. And then down, we'd have V2 minus 6 volts over 1 ohm. Again, that's because we know at the bottom it's 0, and then it goes up 6 to get there. So then we have two equations, and we need to solve them. I'll actually go through some of this math here now. So I'll start by simplifying V1 a bit, or the first equation. So we'd have V1 over 2 plus V1 minus V2 over 2 equals 2. If you want to make this look better, multiply everything by 2. V1 plus V1 minus V2 equals 4. 2V1 equals 4 minus V2. I'll leave it like that now, see if we get something that looks nicer for the other equation. So we have, if I multiply everything by 2 in this equation, we're going to get V2 minus 10 plus V2 minus V1 plus 2V2 minus 12 equals 0. If we add the constants to the other side, you get 24. And then there are 1, 2, 3, 4 V2s. And so we have 4V2 minus V1 equals that. And then, okay, actually I'll move. Hmm. How will this look nicest? Yeah, if this is V2 equals 4 minus 2V1, then we can plug things in here. Let's see. Hmm. Make sure. Oh, I might have messed up my math somewhere. Oh yeah, that's not 24, that's 22. Oopsies. Yeah. V2. Yep. So then we have 4 times 4 minus 2v1 minus v1 equals 22. This is definitely not the best way to do the math. This is just how I'm doing it right now. So then subtract 16. Oh, you get like really weird numbers, I think. Yeah. Um, what, this is like -9. Oh, I definitely messed up somewhere. Hold up. See, this is where the class gets annoying because now you have to do algebra and now you'll actually mess up. However, as long as you get these equations right, you'll get most of the points right on a quiz. Just letting you know. So, what did I mess up here? 2v1 minus v2. Yeah, 2v. Okay. Let me 2v1 minus v2 equals 4. And then this one can be simplified to uh, minus v1 plus 4v2 equals 22. And then if we yeah, and we're trying to find v1 from that first part. So if we want these two to cancel, if this is equation 1 and this is equation 2, if we do equation 2 minus or plus 4 times equation 1, we'll get yeah. So that we'll get this one, so minus v1 plus 4v2 equals 22. And then we will add that to 8v1 minus 4v2 equals 16. You get 7v1 equals 38. And then v1 will be about 5.43 volts. And then finally, to find that power that we wanted earlier, P equals IV. We know I is 2. And then the voltage, as we defined earlier, is 10 minus that V1. We just found V1. So that's 5.43. And then that will get us 9.14 watts. So that's how you do something like that. So again, the part where you'll mess up is in the algebra. However, since this is a circuits class, not an algebra class, assuming you get most of this right, assuming you write these equations correctly, which should be easier than doing the algebra in my opinion, then you'll get most of the points. This is the part where you'll mess up. This is the part that takes a while to grade. So don't feel too bad about that part, but practice your algebra nonetheless if you want full points. So yeah. I have 5 minutes left. So instead of starting another question, I'll just ask if anyone needs clarification on anything. Question mark. Okay, in that case, I think I will stop the recording a bit early, and good luck to all of you on your quiz tomorrow. And yeah, bye-bye.